So now I would like to welcome Marko Pranjić, who will present our joint paper on automatic morphological segmentation for Slovene. So Marko is from Jožef Stefan Institute, a PhD student working on this topic.
So welcome everyone. My name is Marko. I'm a computer scientist without any formal training in linguistics. So this talk is more from a point of view of a person that works with data, that works with text, and tries to solve some practical problems that we encounter. So welcome. The title is Development of Automatic Morphological Segmentation for Slovene, and in it I will present some approaches that were previously done and some of our work where we tried to improve on morphological segmentation. So for first slide, what does morphological segmentation mean to me from my point of view? So, or in a related work in computer science, it is basically development of a system that can automatically split words into morphemes. So we present a word to the system, and it returns some segments of this word that have separate meanings. Although this is probably completely clear for all of you here, it was something I had to learn when starting on this. So in our work, we consider two different types of morphological segmentation, so-called canonical segmentation to canonical morphemes and segmentation to surface-level morphemes. So in this lower part of the slide, you see the example of an English verb writing segmented in those two types of segmentation. So if we are segmenting it to canonical morphemes, then each morpheme needs to have the source. So it's segmented as a write and eng, or writing is combining write plus suffix. In surface-level morphemes, we are interested only in segmenting this word that we got into some parts that can be strictly concatenated. In effect, we are trying to detect the boundaries between morphemes in the surface level of the word. So, why is this important for me as a computer scientist? I know, so for a linguist that works with a living language, morphology and morphological segmentation has much more value. But for me as a computer scientist, I see improved results with systems that use morphological information throughout the literature. For example, those computer systems often have issues with words they didn't encounter before. So in some training data set or novel word that was introduced, we call it an auto-vocabulary word, and computer systems can just say meh. So this is very important for morphologically rich languages where you can probably never cover all the variations of words that you can encounter in the text. It has also been shown that morphological segmentation improves many tasks in natural language processing, and just by including this morphological segmentation we get extra accuracy basically for free. It also improves training of large language models that are now a cornerstone of natural language processing. So a short slide with data sets that we used in this work and that we tried to leverage in developing automatic system. So in the previous slide, we already met all of those. So it's a Slovak lexicon. It's a very clean data, manually verified with around 100,000 lemmas. Metafeeda corpus, which is noisy data, automatically collected. Even after filtering, it has around 1,200,000 lemmas. And of course, the derivational dictionary of Slovenian by Professor Stramljić-Breznik. The dictionary that, although it begins on letter B, contains almost around 10,000 lemmas. There is no explicit morpheme information in this dictionary, but we can use some rule-based approach to approximate it. For example, for an English example, health, healthy, unhealthy, we can try to guess where the morpheme boundaries are in the final word unhealthy. And we did this with this approach, with this data to try to get the explicit morpheme information. So how is automatic morphological segmentation done in computer systems? There are basically two different approaches. One is we don't use any morpheme information. For it, just load a large amount of words and wait for the system to figure things out, to combine words that are similar, try to detect where are prefixes, where are suffixes, and then give us some result. And there is other system where we provide explicit information. During training, we give it a word, say, this is a morpheme, this is a morpheme, now try to see patterns, how to apply it in similar way. And for this supervised approach, where we have some morpheme information, up until this year, all of the systems relied basically on the same technique, on this CRF or conditional random fields. Although it's a slightly older method relative to the development of models in computer science, all of them are still used. For example, this BLSTM approach was also used in our work last year. We developed this final LLM segment that doesn't use, that moves away from the conditional random fields and is a new approach that leverages large language models. We will get to it. I will just try to explain what's a problem with those CRF-like approaches on an example of word unhealthy. So for this system, we have to present the word as a collection of letters. So each letter is separate. It's a sequence of letters, and each of those letters needs to be assigned where it lands in the corresponding morpheme. So, for example, the final letter Y in unhealthy is a single morpheme, and it's marked like that, while all others have their beginning, end, and middle of the morpheme. Well, don't forget that it's just numbers all the way down. So in this first row, we have some vocabulary that's relatively small, around 30 letters, and we have some classes that are predicted. So working on letters prevents us from many things. For example, using large language models. Some large language models are becoming now very popular due to ChatGPT, but we've been using them for a long time. So this approach of ZR is a novel application of pre-trained language models to sub-word level task. We take a word, we try to introduce a boundary in each part of the word, and then guess if this is a correct place to place a morpheme boundary or not. And we show improvement over competing methods in several languages, including in low resource scenarios. So just a short reminder or intro how the large language models work. So they take a complete word and they split it into parts that they know how to work with. The problem here is that we do not have much control how these parts are going to end up. For example, for a word unbounded, it already produces morphemes that are correct. For a word discard, it splits them in two parts, but this split does not correspond to morphemes, or words like fishing that are frequent enough to be included as a complete word into the dictionary, into the vocabulary of the model. So all of those boxes are represented by a single number in the model, and it's hard to find a way how to chop it up and get the model to work. So we modify it by inserting a special character in each position of the word, and try to teach the model to guess which of those are correct. For example, for this word unbounded and the different places where the break is inserted, we teach it, this is a wrong place, this is a correct place, and finally we can union all of those predicted boundaries into our result. So these are short results that we presented this year on LREC conference. We improve on many languages. You can see just for Finnish there is slight distance from the best method, but we use much less data. Our model is conceptually simple. We use just large language models plus 900 words to train the model, and we compete favorably even to this chipmunk model that contains a spell checker, a list of common affixes, and a bunch of other things to get the result. So we are still working on this method, and there are probably some other ways we can improve it. So results on Slovene data using the dictionary on B. We show that, so here are results also by using models that do not use morpheme information, like this morphesser and morphochain. The results are rather low. So when using just a small amount of training data with this BLSTM conditional random fields, we get a significant increase in F1 score and accuracy. And by using our approach, we can improve it even further. So one problem with the data in this evaluation is that the data was generated automatically, so some examples are not correct. From these chains, there are many edge cases that were not handled, but it shows us that this model can even better take the patterns from the data and learn how to segment it properly. So also one plus of this model is that it was already pre-trained on a large text data, large Slovene data, for example, Sloberta model and CSC BERT. So even words that were not seen in training or not related to words in training, it has a capability to resolve them. So here are some examples of prediction together with ground truth, and here are some mixes of correct and wrong predictions. So you can see where it fails. So, for example, in this second line, we see that the first mistake is visible also in the second line, but all in all, it got a feeling for the task, and we are actually pretty happy with the results, and we think we can also further improve it and use it in some other applications. So from my point of view, morphological segmentation provides valuable data and results for computational linguistics and enables more sophisticated modeling of language phenomena. We have seen a lot of references and related work on this line. So with this work, we achieved state-of-the-art for Slovene and several other languages, including languages with a very low amount of data. Some of the results shown were on African languages that are very low resourced. So our next steps are to develop a more specific gold standard data for Slovenian that includes, sitting behind the text and annotating it manually. Train and evaluate multilingual models in line with findings from related work, where it was shown that related languages trained together improve each other in morphological segmentation. And finally, we plan to use this morpheme information on word formation analysis and reconstruct those chains from B dictionary that were shown in the last two slides. Thank you. Are there any questions?
Thank you, Marko. Yes, so we have questions. Roman, please.
The big evaluation table, I wanted just to make sure. So that was, these tables here. This is comparing your segmentation to some ground truth that was manually annotated.
Yes. So this is data from several, shared tasks that contained annotated data that's public, and we can evaluate it.
You mean like more for challenge evaluation?
Yes.
Okay.
Exactly, more for challenge.
I thought it was just for Slovenian, so this is for...
No,
it's all different languages, yes, of course.
Yes, so we develop it first with some known data, because we are not really sure of the accuracy of this Slovene data we constructed with automatic rules. So we evaluate it first with some data that's known to be correct.
And because these are public data sets for Slovene, we will try to make a new public data set, because the other one, it's not public. There was another question, I think. Yeah, please.
Good morning. Thank you very much for a very interesting presentation of your project. It's huge. I was wondering, you showed us that you start with the letters. I understand that it's taken all from the written form of the language, from vocabulary, so that letters. Is there any concern about the relation between a letter and phoneme? Because, it's not only one-to-one. That's one question. And the other, following or continuing in this idea, morphemes. Do you, again, I guess that you take just the dictionary representative form of the word, like in nouns, nominative, singular. But in morphemes, and not only in declination, but also in word formation, there are allomorphs. So this is something which is not taken. Mm-hmm. Thank you.
So part of the question was related to this approach. This is a slightly older approach that we tried to improve on, and we moved on from letters. So we are not using letter by letter approach anymore. So now modern language models have, they call it vocabulary. Those parts of the words they found statistically frequently, and they included as subparts of all words that they can represent. For example, the word fishing is a single vocabulary item, while discard is composed of two, disc plus ard. So I'm not sure if this answers your question there. So one part is also morphological segmentation is not one-on-one, but just by looking at the word, you don't know where are the morphemes. You are like a bit of a context. So the model we are using, large language models, is training on a large amount of text, and one of the strong points of it is taking in the context. It's still an open how we will do it, but it should be possible. We are not constrained in any way to include the whole sentence in it and just segment the target word, or include some usages of this word and get the result. I'm not sure if this answers your question.
And I think for the second question, we have to be brief because we are running out of time. But I think in general here, as it's a supervised approach, it really depends what you take as training data, right? So if nominative is in the training data, the models are focused on that. But if the training data is different, then it would expand. I think that's a brief answer, right? Or no, you can object.
Basically, yes. The model will learn the best what we present him with most examples of. And if these are cases of the same word, it will learn how to split it. If it's just a nominative case, it will focus on that. But we can also continue discussion.
Yeah, thank you, Marko, very much.